We keep hearing that flip-flops can become metastable, and now we get to see that that really is the case and why that occurs. We have seen how to make a flip-flop, and the crucial part is our Rs Latch, which in this case I'll use 2 NOR gates. That's R, that's S, this is Q, this is Q prime, and we discussed this before in lectures, and we know that when both R and S are 0, then each of these looks like an inverter. And so we end up with, if I unravel them, this circuit here. And this is what gives us memory, because if the output is currently a logic 0, then 0 comes around here, it becomes a logic 1, it becomes a logic 0. Self-reinforcing, it can remember logic 0. It can also remember logic 1. If this is a 1, then 1 comes around here, logic 0, logic 1, self-reinforcing. So we have 2 stable equilibria. Either I have 0 coming out and it stays 0, or I have 1 coming out and it stays 1. And it's stable because even if noise means the output is not exactly 1, it's a little bit less. When it goes around, this will clean it up, this will clean it out. I get a very nice clean 1 coming out again. So both 0 and 1 are stable points of this circuit here. We're going to make this precise because this circuit is the key to understanding flip-flops. And no matter how you make a flip-flop, whether you use transmission gates or you use the way we learnt in lectures, where you start off with an Rs latch, then make a D latch by putting some combinational logic out the front, then using a master-slave, 2 D latches in master-slave combination, you can end up with a D-type flip-flop. So it doesn't matter how you build it, basically you've got 2 inverters at the end that's doing the latching, and we'll analyse this circuit now. To analyse this circuit, we partially remove the feedback loop and we fill it in with just a dotted line to remind us that it is actually closed, but we want to analyse it without that feedback loop there. And then what we do, if I call this voltage A and this voltage B the input-output, I can get a graph where if A is here, the voltage at A, this is the voltage at B, and we can show, if we analyse the FETs, that the response of this buffer looks pretty much something like this. So here we've got 0 volts, depending on the supply rail, maybe I make this 5 volts, and I make that 2.5 volts. And this is part of the fact that logic gates clean up noise that we've discussed earlier. So even if the input voltage is quite far away from a logic 0, when we get to the output, we're forced back to being very close to 0. Similarly, if the input is far from a logic 1, when we get to the output, we find we're very close to a logic 1, because logic gates tidy up noise. As we will see presently, it's most useful to draw a line at 45 degrees through this graph here. And this allows us to work out how this circuit works. Along this dotted line, imagine that there's a small delay. So we put a voltage at A, it propagates through to B with or without a delay, doesn't matter for this argument. Then there's a small delay before being fed back to the input. And so this means that this circuit could oscillate, or it might converge to an equilibrium point. An equilibrium point is when I put in a voltage here, it propagates through here, gives me another voltage, and this voltage is exactly the same as my input voltage. So I have reached equilibrium with no more oscillations. So the first thing we'll do is we ask, what are the equilibrium points of this circuit? That is, what input voltage will give me the same output voltage here? And we find that there are precisely 3 equilibria here. If I put 0 volts in, I'll have 0 volts coming out, that's consistent. If I put 5 volts in, I'll have 5 volts out, that's consistent. And here's the metastable state. If I put, let us say, 2.5 volts in, I'll have 2.5 volts coming out. And that's also an equilibrium point. No more oscillations. There's a big difference though between this point and the two endpoints. We'll see presently that the two endpoints are stable. In fact, we discussed that just before, but we'll show it another way too graphically. A bit of noise is not going to influence what happens. If there's some noise going through here, then it gets tidied up and we get pushed back closer to 0 or pushed back closer to a logic 1. So these 2 points are stable. This point, however, we will see is very unstable. As soon as we pushed a little bit this way, then the circuit will rapidly converge to a logic 1. If we pushed a little bit this way, the circuit will converge quickly to a logic 0. That's why we normally exit from a metastable state quite quickly. But we can actually show this graphically what happens. Although this transition is relatively realistic, in order to emphasize what's going to happen and to make it easier for me to draw, I'm actually going to change this to be less steep. So it normally is this steep and we get fast convergence to 1 or 0, but to allow me to show you what happens, I'm just going to modify this quickly to something less steep in the middle. Here's a bigger figure, and along the bottom we've got the input voltage going up the side, we've got the output voltage. How does this work? Let's assume the input voltage is at this point here. What happens when we go once around this loop here? Well, this is the input voltage. What voltage do we get at the output? That's easy to find out. By definition, that's the red curve. So I go up here, straight up, I go straight up, and I find, this is the voltage I get at the output, if this is the input voltage. So now I want to know what happens if this output voltage is fed round and becomes the input voltage. So whatever value this is, and we find that out by going across here, if this voltage were, for example, 2 volts, then I'd want to come down to this axis here and find 2 volts and repeat the process. Now I could do that way, but that's not very graphical. Instead, there's a graphical way of doing the same thing. Notice that all I need to do is move across to the green line. And we see, had I drawn this perfectly, that the point of intersection here is the same as the point we got using the simple method. And the reason is because this green line should be at precisely 45 degrees. And so it allows us to go from this axis to this axis. So let's do this again. Assume this is the input voltage. We go up to the red line to find the output voltage. Now I want to read off the output voltage, say it's 2 volts, and go down to the same positions, 2 volts, on the input axis. To go from the output to the input, well, this green line does that. It does the reflection for us. So if I want to go from a 2 volts output to a 2 volts input, I go across to the green line and then go straight down again. So I end up just going straight up to the red curve, across to the green curve. Now this is the same as having gone to the input here. So now we want to know if this is our new input value, what's the output value? Well, we know that we go up to the red curve, but this intersection point at the green one is the same as down here, so I just go down from the green curve to the red curve to get the same thing. So that means that after one cycle, I now go down, and this is my new output voltage. And I repeat, if this is my new output voltage, then I go across to the green line to map it to my input voltage. This is now my new input voltage, which when I go down to the red line becomes my new output voltage, becomes my new input voltage, my new output voltage, my new input voltage, my new output voltage, my new input voltage, and I'm driven to 0 in just a few iterations. And similarly, had we initially applied an input voltage up here, then that means that my output voltage would be here. My next input voltage is therefore at the green one, which leads to this output voltage, which leads to this input voltage, which leads to this output voltage, and very quickly I've converged to a logic 1. This rigorously allows us to see that even if we have some noise perturbation, then this circuit will push us back to a logic 1 or push us back to a logic 0. And I drew this to be smoother, remember. Normally we have a very sharp transition, and so you almost immediately go to a 0, almost immediately go to a 1. The middle here is the opposite of stable. It's unstable. It doesn't matter how close we start to the middle. I can try to start very close to the middle here. I go up. But unless I exactly get the middle, I'm going to end up a little bit to one side of the middle or the other. And if I end up a little bit to this side, then when I go to the green line, I'm even more on this side. And I go to the red line, I'm even more on this side. And you see quickly we escape from the center point and head off to either plus a logic 1 or a logic 0, depending on whether we get knocked a little bit this way or a little bit that way. So we have got 2 stable equilibria and 1 unstable equilibria. If we do somehow get stuck here, the tiniest of bumps will push us one way or the other, and that's enough for this feedback loop to then drive us to a logic 0 or to a logic 1. In case you think all this is theoretical, let's have a look at our textbook, Daly and Harting, Digital Designer Systems Approach. They actually built a physical circuit here, physical digital circuit, and it's used to demonstrate metastability. And if we go to the next page, this is the output of a flip-flop averaged over 1 second. I believe the clock frequency is about 150 kilohertz, so 150,000 times we have our flip-flop potentially becoming metastable. We see that this is the halfway voltage. We have got a logic 0 here, a logic 1 here. The flip-flop is getting stuck in a metastable state for a certain period of time. Sometimes it leaves early, either to 0 or to 1. Sometimes it leaves a bit later. When it leaves the metastable state is unpredictable. Now this circuit is designed to vary the timing on the inputs to try to drive the flip-flops to a metastable state. So that's why we're actually seeing it occurring relatively often. The key point is that the time it takes to exit from the state is random. The closer we end up to the halfway point and the less noise there is, the longer it will take to leave the metastable state. We saw that in our analysis on the previous slide. This figure is essentially the same as before, but this time over a period of 1 hour. So we have many more examples, and we see that sometimes we can get a very long period of time inside the metastable state. There are some times within the hour when we entered the metastable state and stayed there all the way up until this point in time. And then sometimes we went up to a logic 1 and sometimes to a logic 0. So it really is random when we leave the metastable state, and it's random whether we end up at a logic 1 or a logic 0. I have here a D latch, which we will examine in a second. The 2 capacitors here signify that it is going to be driving some other logic gates in practice, and its inputs are basically various pulses that I've chosen to give us some interesting outputs to look at, and we'll be performing a transient analysis, so to see what happens in real life, so to speak. If I double click on the D latch, we see that we make a D latch out of an inverter, 2 NAND gates and an Rs latch. The inverter, if I double click on that, is the usual inverter made out of 2 FETs. If we go back to the D latch, the NAND gates are again made out of this time 4 FETs in the usual way, and the Rs Latch is made up using this time 2 NAND gates, and we saw the NAND gate from before. Each NAND gate is made from 4 FETs. Going back to our circuit, we wish to simulate it. Hit on the running man. The gate or enable pin looks like this. When the gate is a logic 1, then whatever is on the D pin should flow through to the Q pin. When the gate drops, the D latch stops continuously photographing the input, and the output remembers the last value that it saw at the input. The data pin here looks like this, and notice that here and here we have got the data pin changing very close to a changing gate, and that's often a recipe for getting metastability when the gate is turning off, going from a 1 to a 0, and we'll see that presently. The output Q here looks like this, and right here we have metastability. Let's zoom in and talk about this in more detail. So G for gate or enable, the green line is a 1 up here, so the output, which is red, is just a copy of the input, which is blue. Same up here, the gate pin green is a high here, so the output red is just a copy of the input blue, the data input here. What's of interest is when the gate turns off, which is here, the gate goes from 1 to 0, and also down here, the gate goes from 1 to 0. Let's look at the first case first. The data input, this blue line, is initially a logic 1, then it drops to a logic 0 down here. Just after it drops to a logic 0, the gate drops down to a logic 0. So what happens when the data drops down? Well, the input FETs have got a capacitance. They're initially at a logic 1. When the data pin drops down to a 0, that's causing the input capacitances to discharge to 0. And that will cause the output Q to start to head towards 0. However, before it's fully discharged, the gate turns off, and that then stops the input from discharging the capacitance. And in this case, the value at the output hadn't quite reached the halfway mark, and so when the discharge current has turned off, it just turns around and heads back to a logic 1 because it hadn't passed the halfway mark, so to speak. When the gate is a 0, remember the D latch at the Rs Latch side at the end, it just looks like 2 inverters connected in series. And so with 2 inverters connected in series, the output will either head up to a logic 1 or down to a logic 0, depending on which side of the border that they start off at, so to speak. Over here though, after many attempts at choosing just the right duration between when the data drops to 0 and when the gate drops to 0, we can achieve the effect that once the gate drops to 0, the amount of discharge has brought us almost exactly to the halfway point. And if we're at the halfway point, then, if you like, the double inverters don't know whether to go up or go down. They just stay where they are until noise, or in this case numerical error, perturbs you one way rather than the other. In this case, we get perturbed downwards. And as soon as we start heading down, then it's not long after until we get pulled all the way down quickly. So from here to here, roughly speaking, is where we're stuck in the metastable state. We're not stuck if we immediately return to a logic 1 or drop all the way to 0. And both these states are valid in the sense that if the input dropped to 0 earlier, then the output should drop to 0 earlier. And if the input dropped to 0 later, then the output should stay a 1. So depending on whether the blue one arrived a bit earlier or a bit later, both outputs are perfectly fine. Over here, we're stuck at the halfway point though. In theory, it could be arbitrarily long. In practice, random noise coming from heat and other things will quickly push us a little bit one way or the other, and then we quickly get pulled to a logic 1 or a logic 0. For completeness, there's one other circuit we look at completely. Here we have just got two inverters, and remember, when an Rs latch is in the latched state, then the output of this inverter gets fed back to the input of the first inverter, and that's what gives us memory. It just keeps remembering what its output is, and it stays like that. Here we're going to compute the steady state transfer function of two inverters to see what they are, a DC analysis. So we run this, the input is just going to rise up, and if we look at the output, we get this very nice sharp transition here. So this is close to being, each inverter is close to being an ideal inverter. We have two of them together, we get a buffer, and if the input is a logic 0, the output's a logic 0. If the input's a logic 1, the output's a logic 1, but we really tidy up the signal. So even if we have a fair bit of noise on the input, it still gets pulled down to a logic 0 or pulled up to a logic 1 with this very nice sharp transition here. Now in terms of analyzing the Rs latch, the key point to look at is if we connect the output all the way to the input, when do we have consistency? When can I join the output to the input and stay in steady state? Well, that means we're looking at points in this diagram here where the output voltage exactly equals the input voltage. And if we look carefully, we see there are three such points. There's this point down here. If this is a logic 0, that's a logic 1, that's a logic 0, which is consistent here. And there's a point up here. If this is a logic 1, that's a logic 0. This is a logic 1, which is consistent with the logic 1 here. But there's also this metastable point in here at roughly the halfway mark. If our P channel and N channel FETs were perfectly symmetric, then it would be precisely in the middle, but we don't have to worry about that. The point is, it doesn't matter what's happening. If I have got a green line going at 45 degrees from here to here, and my blue curve has to be below the green line here and above the green line here, then simple topology tells us it has to cross the green line at some point. And this gives us a third point at which we get consistency. So theoretically at least, if I take this intersecting voltage right here, if I put that voltage here, then I'm going to get exactly the same voltage here coming out. That's what this graph's telling us. And so if I connect it back to the input, then in theory this circuit will just stay at that voltage at the input and the output. So this is the third equilibrium point. Unlike these two equilibrium points though, this one is not stable. At this point here, even if we add some noise here, if we add some noise, by the time the noise goes through these two inverters, at here the noise goes through the inverters, at this point the noise goes through the inverters, the output is going to be pulled down to almost 0 volts. So that brings us over here. And so very quickly we end up either down here, or if we're up over here, if the input's at 2.4 volts, then that means that the output is going to be very close to 3.3 volts, which brings us down here. And so very quickly we end up at this corner here. However, if we start our system at this 1.7 volts or whatever approximate value, then if we get pushed slightly this way due to noise, we're quickly going to end up here. If we get pushed slightly this way due to noise, we quickly end up down here. Hence this is unstable, but these two are stable.